everybody. So in this video, we're going to go over some examples of using the mean value theorem. Okay, so the first example we're going to look at is just a basic example of how the mean value theorem works in terms of checking the hypotheses, and then looking for that C value that is guaranteed by the theorem. Okay, so let's look at our example. Okay, so we want to check that our function square root of x is satisfying the hypotheses on the interval 0, 4, and then we want to find the C that is guaranteed by the theorem, right? So if we forgot what the mean value theorem is, that's up here on the top left-hand corner. So let's go ahead and check those hypotheses, okay? So we want to check that square root of x is continuous on the interval AB. Okay, now we know that square root x is continuous on its domain, right? But that's not really what you want to say. Almost a lot of functions are continuous on their domain. We need to be specific about what that means for this function, okay? So we want to say that f is continuous, okay, on what interval? So what interval is this function continuous? Okay, so this is the interval 0 to infinity, okay? And then we specifically want to mention the interval from the question, okay? So we would say specifically right, f is continuous on 0, 4. Okay. Then we want to look at the derivative to talk about where the function f is differentiable. Okay, so we'll look at f prime of x, right? So f of x is x to the 1/2 power. Okay, so f prime of x is going to be 1/2 x to the -1/2, right? Which could also be written as 1/2 square root of x, okay? So this function is defined right? So we have two different things going on about the domain here, right? We have that x is in the denominator, right? Meaning that we don't want the denominator to be 0, okay? And we also have that x is in a square root, meaning that we want x to be non-negative, okay? So we need x to be non-negative, but also if you plug in 0, you are going to get 0 in the denominator. So f prime of x is defined for the interval 0 to infinity, right? Not including 0, okay? It's only defined for non-negative values because of the square root, right? But it's also not defined for x equals 0 because it's a rational function in which 0 in the denominator would make it undefined, okay? So f is differentiable on the open interval 0 to 4, okay? Now, we can see that in this example, this function is definitely not differentiable at 0, right? The derivative is actually undefined at 0, but that's okay because we only need it to be differentiable on the open interval 0 to 4, okay? So that's the first part here, right? We want to check that f satisfies the hypotheses. These are the two hypotheses, and we have checked that. Okay, so now we want to find the c guaranteed by the theorem. Okay, so that would be telling us that f prime of c is equal to, right? In this example, b is 4, so this would be f of 4 minus f of 0 over 4 minus 0. Okay, so f prime of c, that is going to be 1 over 2 times the square root of c. Okay, and then here f of 4 is going to be 2. Okay, and f of 0 is 0, of course, right? Because f of x is square root of x. Okay, so I have 1 over 2 square root c equals 1/2. Okay, I'm going to go ahead and cross multiply here. So I get 2 square root of c equals 2. Divide both sides by 2, and I get square root of c equals 1. Okay, so c is going to be 1. Okay, so I want to look at what this means graphically. Okay, so remember, we talked about this in the last video, right? This thing on the right here is the slope of the secant line, right? The line between the 2 points 0, 0, and 4, 2, okay? And this is saying that at this point C, right, so at x equals 1, the tangent line is parallel to that line, okay? So let's look at what that looks like. So here's a graph of square root of x, okay? And then let's look at the secant line, right, or the line between the 2 points, okay? So this is the line between the 2 points 0, 0, right, and 4, 2. Okay, so you can see that line there. Okay, then we want to look at where the tangent line is going to be parallel to that. Okay, so let's look at the tangent line, and starting at 0, 0, right, we want to see where this line is going to be parallel to the tangent line. So if we kind of scroll through these values, right, we can see how at some point it has to be parallel here. And for us, right, you can see that it's exactly parallel right here at this point, right, at exactly 1. Okay, so you can see how these two lines are parallel at that point. Okay, so that's the graphical idea of what's happening here with that theorem. All right, let's look at another example. Okay. So for this example, we're going to look at the function 2 minus absolute value of 2x minus 1. Okay. So what we want to do is show that there is no value c so that f prime of c equals f of 3 minus f of 0 over 3. Okay. And then the second part of this is, why doesn't this contradict the theorem? Okay. So let's go ahead and look at this. So the first thing we're going to do is try to show that there is no value c, so that f prime of c equals f of 3 minus f of 0 over 3. Okay, so let's go ahead and look at f of x written as a piecewise function, okay, so that we can actually tell what's going on here. Okay, now if 2x minus 1 is positive, right, if this is positive, then what we know is happening is that the absolute value is doing nothing, right? So this is just going to be 2 minus 2x minus 1, right? If your number is already positive, the absolute value doesn't change that number at all, right? So we can just take out the absolute value, okay? Now, if 2x minus 1 is negative, okay, then we know that the absolute value changes the sign, right? So this would be 2 minus negative 2x minus 1. Okay. Right, if 2x minus 1 is already negative, then this negative sign is going to change it to a positive. Okay, so let's simplify that a little bit. Okay, so first of all, this is going to be minus 2x, right, plus 3. Okay, and then here, this minus minus is going to be plus, right? I'm going to have positive 2x, okay, plus 3. Oh, I'm sorry, minus. So I have, this is turning into a positive, so this is 2x, this is just 2 plus negative 1, so this is just going to be 1. Okay, now we even want to simplify the conditions here, right? We want not to say something about 2x minus 1, but to say something about x. So if I solve for x here, right, adding 1 to both sides and then dividing by 2, this is going to be x is greater than 1/2, right? This we can include, right? And then here, this would be x is less than 1/2, right? Again, adding 1 to both sides and then dividing by 2, okay? So that's how this function looks as a piecewise function. Okay, so I really suggest, if you're starting out, to write it out like this, and then you can always simplify it, right? All right, so now let's look at the derivative. Okay, so the derivative is also going to be piecewise, right? So in the top condition, right, if x is greater than 1/2, we know that the derivative is going to be -2. And in the bottom condition, where x is less than 1/2, we know that the derivative is going to be +2. Okay? All right. So then let's go ahead and look for this given value. Okay? We want to look at f of 3 minus f of 0 over 3. Okay? So this is going to be 2 minus the absolute value of 2 times 3 minus 1 minus, put that in parentheses, 2 minus the absolute value of 2 times 0 minus 1 over 3. Okay, so 2 times 3 is 6, minus 1 is 5. The absolute value of 5 is 5. Okay, 2 times 0 is 0, minus 1 is -1, and the absolute value of -1 is +1. Okay, so this is going to be -3 minus 1 over 3, or -4/3. Okay, so you can see that there is no value where the derivative is going to be equal to -4/3, right? The derivative is either -2 or +2. It is never -4/3. Okay, so what we need to do is write out a sentence to explain that. Okay, so f prime of c is -2 or +2. Okay, f of 3 minus f of 0 over 3 is -4/3. So f prime of c, right, is never equal to -4/3. Okay, it's just not true. We can see what the values of the derivative are. We can see that this value is not the same. Okay, now the second part of the question, right? That answers show that there's no c value that this is true, right? That's just not possible. You can only get -2 or +2 for the derivative. You can't get -4/3. Okay, so why doesn't this contradict the mean value theorem? Okay, right, this is the end result of the mean value theorem, right? That this should be true, right? So why don't we have this? Okay, so we would be talking about, first of all, the interval 0 to 3, okay, and the function f of x that's given. So if you look, f of x is continuous, right? We know that absolute value functions are continuous and constant functions are continuous. So the difference between them is continuous. That's not the issue, right? This is a continuous function. The issue is the second part of this, right? The differentiability. You can see that at exactly 1/2, where the vertex of this graph is, this function is not differentiable, okay? So f of x is not differentiable at 1/2, okay? So what that means is it's not differentiable on 0, 3. I should say on 0, 3, right? On the interval 0, 3. Okay? So it doesn't meet that second condition, all right? The theorem does not apply. Okay? And again, this is another example of why it's so important to check the theorem's hypotheses before you conclude, right? You can't just apply the mean value theorem to any function, right? Or even any familiar function, right? You need to check both of the hypotheses carefully for the interval that you're interested in before you apply the theorem.